Let's get ready to do some math. 11 honors, how you doing out there? Okay, another pre-calculus instructional video starring you, the students. Okay, day 2 right here. So what are we on? Wednesday here. I didn't even say yesterday. I hope that you had a pleasant Memorial Day weekend. But whatever. Anyway, we talked about yesterday. What did we talk about? What's that word? Starts with R. Recall. Okay, and we talked about the definite integral. So recall the definite integral. The definite integral. And really, we talked about the theory behind it. We talked about how it gave you the area between a function and the x-axis. We're going to talk about that a little bit more today when we go over the homework, but we're going to try to focus more on mechanics of just doing different types of definite integrals. Okay, but remember, we say the integral from a to b. I'll say of f of x with respect to x. That's that main difference right there between the definite integral and the indefinite integral. You have those bounds right there. We know if you integrate little f, we say big F of x. Don't put the plus c. They're going to cancel out. Okay, we're going to evaluate this from a to b, and that means we plug in the upper bound first, and then we subtract the plugging in the lower bound. It's actually the fundamental theorem of integral calculus part 1, version 1. Some people stop right there, but it's wrong if you do. You got to say where if you take the derivative of big F of x, you get little f of x back. Just that disclaimer. Once again, the better way to write it is to say that you're actually integrating a rate of change, the integral from a to b of f prime of x with respect to x, because then we know we get back f of x, evaluate it from a to b, and that's f of b minus f of a, okay? And it's just giving you a number, a numerical value. It's actually, it can represent the area, can represent something that's not area. What it always does is represents the change between two y values. And if you start, you're going to function over here. I don't know. We'll say this is A and this is B. Okay, and here we'll say the y value is 2. And here we'll say the y value is 5. If you actually want the change in y values from A to B, well, that would just be 5 minus 2. And that would give you a change of positive 3, which means you just went up 3 units. That's all it means, okay? But you could see that you had to do the later y value. That was f of b, right? Because of the point b comma f of b. So you had to take that later y value minus the previous y value, a comma f of a. If you want the change between two y values, always take the later y value, subtract from it the previous y value, okay? And that's going to give you that actual change. Even if it went down, if you had a function, I didn't really plan to do this, but whatever. Okay, it does something like this, okay? And maybe a is here and b is here. Now we can see f of a is equal to 6. We'll say b is equal to 2. What's the change in y values? Well, if you go from 6 to 2, you went down 4 units. So it's a negative change. The change in y value is actually negative 4. And that's what would happen if you do the later y value, which is 2, minus the previous y value, which is 6. That's going to give you that negative 4. A change can be negative. If something gets bigger, a change is positive. If something gets smaller, a change is negative. That's the reason you plug in the upper bound and then subtract the plug in the lower bound. You still might not have any idea what I'm talking about. That's fine, okay? Just remember to actually do it that way, and eventually we'll get there, okay? As far as the homework was concerned, hopefully not too bad setting these up, okay? Make sure that you could evaluate these by hand, that you can graph by hand for 1 and 2. Shouldn't have been bad. 3 and 4. 3 is more annoying to graph by hand. It can be done, okay? You could do number 3 right there by getting domain. It's just a linear under a radical. This one, pretty rough to graph by hand, so don't worry about that. And look, you had the calculator, okay? All you had to do is actually set up the integrals, and then put them in the calculator. Little, math 9. Okay, so make sure you practice that and you're good with that. It's pretty important, okay? But it's also important, very important, to be able to integrate by hand. So make sure on the quest, if it's a problem where you have to integrate by hand, where it says show the integration process or show work, make sure you show that work. That is very important, okay? One final thing, yes, you can only use the definite integral to get the area between a function and the x-axis for now when the region lies above the x-axis, which is what's always happening here in these problems, okay? And if the region is below, it's actually a negative answer. An integral can be negative, an area can't be negative, things that we'll speak about. But let's do some more mechanics today. Okay, and if you want like a topic sentence, yesterday was, the definite integral we started speaking about. We're going to continue with the definite integral. You could call it day 2. You could also say U-Substitution is going to be involved, but it's not all U-Substitution. So really, it's just the definite integral day 2. And let's take a look at this problem right here, because this is a U-Substitution situation, okay? If you want to integrate something like this, I hope you realize that you're like, oh, you know what? This is really the integral. We still got it from 0 to 4, but last chapter there weren't bounds there. We took the 2x plus 1 and we raised it to the 1/2 power with respect to x. And remember, if you want to integrate, you know, a function and it's a variable base raised to a numerical power, you could use that kind of backward power rule as long as you got one single letter raised to the numerical power. This is not one single letter, okay? We're going to force it to be one single letter by setting it equal to u. Hopefully you remember your u substitution. It's extraordinarily important, okay? Remember, it's always going to be du over the derivative of u, which is 2 here, is equal to dx. And it's funny, because they call it u substitution, but I think they should really call it 2 substitution, because you really substitute two things. You take out the 2x plus 1, replace it with a u. Then you take out the dx, replace it with a du over 2. And I know what you're about to do. You're about to pull that 1/2 out to the side, right? And say that you're done. But the problem is, this is just wrong. People are like, wrong? What do you mean it's wrong? Well, there's an extra little something going on here, and that's the bounds, okay? You know, these bounds right here, I knew they were x bounds. How did I know there were x bounds? Because if I have a dx right there. So that was actually x equals 0 to x equals 4. Not necessary to write that because the dx implies that it's x bounds. But guess what happened in this step right here? It's not a dx anymore. Now it's a du. So you shouldn't have x bounds. You should have u bounds. People are like, how the heck am I supposed to have u bounds? Okay, you really should jump from this step to this step right here. Okay, we know it's u to the 1/2. Times du over 2. But now that we have a du, we need u bounds, okay? And people are like, well, I mean, if x is equal to 0, how am I supposed to know what u is equal to? If only there was some relationship between x and u that we already have identified. And we do, okay? You know, if x is equal to 0, we know that u is going to be equal to 2 times 0 plus 1, which is going to give you 1 as an answer, okay? So this right here is really going to be 1. It's really u equals 1. It's changing that bound. You don't need to write u equals 1 because it's implied, but we'll do it the first time. You know, what if x is equal to 4? Well, if x is equal to 4, and you don't need to show this work. You could just think about it. U is equal to 2 times 4 plus 1, which is going to be 9. So this upper bound actually becomes u equals 9. So what you should really do is when you perform your 2 substitution, believe it or not, it's not just 2 substitutions. It's 3 substituciones, because you need to substitute for a third thing, the bounds. You're going to pull out the 1/2, right? Inside here, you're going to have u to the 1/2 with respect to u. But now I need those u bounds, those new u bounds, the integral from 1 to 9. And what we actually have right here is we have an integral that's equivalent to the original integral. Equivalent to original integral. And they'll do that on the AP exam. They'll give you this integral right here. They'll say, using the substitution, u equals 2x plus 1, which of the following is an equivalent integral? And you'll see this one right here. You know what other answer you'll see? This with a 0 and a 4 right there. You got to change those bounds. Now, there are ways to avoid changing the bounds, which I'm sure people already think about in their head, or they will after I go through this problem right here. But you don't want to go down that road, okay? Believe it or not, it's easier to change the bounds. And, you know, like I said, the type of questions they ask on the AP exam, it's not just about getting these integrals right. You know, they want you to be able to recognize equivalent expressions and things like that. So here, when we finish this up, we still got to integrate here, right? Pull that 1/2 to the side. You just get chill. We integrate u to the 1/2. Add 1 to the exponent, divide by that number. 1/2 plus 1 is 3/2. Rourke is over there dividing by 3/2. The rest of us multiply by 2/3. Don't put the plus c. We're going to evaluate it from u equals 1 to u equals 9. Now remember, these are both u bounds right here. We changed these. You don't need to write it, but it's implied, okay, that u is equal to 1 and u is equal to 9 because there's u inside here. So what we normally would do when we did u substitution last chapter, we take out the u, we put the 2x plus 1 back in. Well, if you do that, if you take out the u and put in the 2x plus 1, then you got to go back to the x bounds. But since these are u bounds, they represent what u is equal to, we can keep the u here. So when you use u substitution with the definite integral, it's all u. I made that up. You don't bring the x back. You know what happens right here? These 2's cancel and make this look a little bit nicer right here. So really end up with what? 1/3 u to the 3/2 evaluated from 1 to 9. You know, some people, they're like, yeah, I'm going to put the 2x plus 1 right there, and then I'll put these back to the original bounds, you know, 0 to 4. You could do that if you want to. But in your steps, you know, if you suddenly put the 0 to 4 here and you still have a u, you don't have an x, you're going to lose credit, okay? You want to be careful with stuff like that. So really what you can do is you could actually integrate it using U-Substitution. You could bring back the x, and then you could use the x bounds, but you got to make sure you don't have a step where suddenly, you know, you have x's there when you have u's there, but you have x bounds. Maybe you want to eliminate the bounds for a step. Technically, that would be unequal, though. So really, changing bounds is the better way to go. It's not terrible. This becomes 1/3, 9 to the 3/2. Let's plug in that upper bound. Minus 1/3, 1 to the 3/2. People get annoyed. They're like, yeah, but Berto, this lower bound was 0. That's easier to plug in than a 1. You changed it to a 1. Well, you had no choice. Even if you took out the u and put in the 2x plus 1, when you plug in 0 for x, you would get a 1 inside there anyway. So what you got to understand is people are like, yeah, change the bounds is more work. It's not. It's the same amount of work. It's going to enable you to be able to answer other types of problems. You know, what does this give me right here? 9 to the 3/2. If you can't do this, you know, obviously you weren't paying attention the whole first half of the year. So square root of 9 is 3. Cube that 3, we get 27. So 27/3, which is 9. I get it, but it's minus 1/3. So I'm going to keep it as 26/3 right there, okay, as far as the answer is concerned. So U-substitution with the definite integral. It's not 2 substitution anymore. It's 3 substituciones, okay? You actually need to substitute for the bounds as well. That's the third thing right there. You know, try another example right here. You can see it's a classic U-substitution situation. You see multiplication going on in here. The base of a numerical exponent of 1/2 is not one single letter. I think there's only one viable U. By the way, you could always try to manipulate algebraically, right, to avoid using U-substitution. There's nothing you could do here algebraically to change the way that this looks, okay? I'm going to get du over the derivative of u, which is 4x, is equal to dx. And now perform first the 2 substitutions, right? This x, he's still there, but not for long. You should have been thinking about that, right? You take the derivative to the inside, you know an x will be generated downstairs to get rid of that x upstairs, so you don't have to worry about it. This is now u. Instead of being under a radical, we'll say it's being raised to the 1/2 power, same thing. Then we'll put a du over 4x. Technically, it's not equivalent, right? Because this is an indefinite integral. This is a definite integral. We need those new bounds. If x is 0, u is equal to 2 times 0 squared plus 1, that's 1. And if x is equal to 2, u is equal to 2 times 2 squared, that's 2 times 4, which is 8 plus 1, which is 9. So just happen to get the same balance that we got in the last problem. It's just a coincidence, okay? You know, and now to set up that equivalent integral, these x's cancel. Look at this disaster. X's and u's frolicking about together. These x's, you have no place here, okay? There's a du. These are u bounds, so they cancel out, luckily. If they didn't, we'd be in deep doo-doo. Be a different type of situation. Pull out that 4. It's not even a 4, right? It's really a 1/4. Bring them out, bring them out. Now we got the integral from 1 to 9 of u to the 1/2 with respect to u. So you've actually forced a basic rule, and this guy right here is equivalent to the original integral, okay? Similar to the problem we did before, I get it. We'll do more interesting problems in a second. Pull the 1/4 to the side, integrate u to the 1/2, add 1 to the exponent, divide by that number. Don't put plus c, there's not necessary right there. But we're going to evaluate it from 1 to 9. We don't need to worry about x anymore, okay? It's all u, like I said before. You're not going to get back an expression in terms of u or x when you're done with this problem because it's a definite integral. You can get an actual number back. Anyway, cancel here, right? Divide by 2 top and bottom. I would. So here we really have what? 1/6 u to the 3/2 evaluated from 1 to 9. Okay, so let's plug in that 9 first. 1/6, 9 to the 3/2 minus 1/6, 1 to the 3/2. And very similar to the previous problem. This gives me 27/6 minus 1/6, which gives us 26/6. If it's multiple choice, you'll probably see 13/3. Remember, a part 2 problem, not necessary to simplify. On an AP exam, you could leave this as the answer, and you will, but not this year, okay? You know, next year we'll worry about that. This year, you got to practice stuff like this because it can be very annoying. This is nothing. You'll see that they get extremely more annoying to calculate, you know, without the use of a calculator. But multiple choice next year, you need to know how to get these answers, okay? So look, it's not something you can just use the calculator for, but you can always check your work. Well, math 9, right? Put this right in the calculator there, hit enter. You should get 13/3 back, okay? The calculator is really cool for the definite integral, but make sure you actually know how to integrate. And interesting things happen with the definite integral, right? Let's get less algebraic. Let's get more trigonometric, a little transcendental action here. This is not a U-substitution definite integral situation. This is basic integration. How do I know? The argument of the trig function is only one single letter, okay? So I don't need to set it equal to u. We know how to integrate sine, right? In a world of integrals, sine is the bad guy. Grink, I believe this knife is yours. He stuck it in my back. He betrayed me. Okay, you know, sine is the bad guy. In the world of integrals, his integral is going to be negative cosine x. No plus c, right? We just evaluated from 0 to pi. People are like, I'm annoyed that there's a pi there. Well, you should like it because we're dealing with trig right here. Plug in that upper bound first. Negative cosine pi. Check this out. Hope you know what? I'll write it down. Minus negative cosine 0. So a lot of people are going to go right to negative cosine pi minus negative cosine 0. So plus cosine 0. Skip a step if you want to. Cosine of pi, if you don't know, it's equal to negative 1. I don't like you anymore. Okay, plus the cosine of 0, we know is equal to positive 1. So really it's just 1 plus 1, yielding the desired result of 2. And yeah, make sure you know those trig values. You know, so definite integral, you know, with different types of functions. You know, this one right here, the real deal is, can you integrate it? You know, the definite integral part, I mean, really, it's just an extension of what we did last chapter, okay? I know it can be annoying, but it doesn't mean you shouldn't actually understand how to do it. Here, cosine x times sine squared x. So what is that? Sine x quantity to the second power times dx. Classic type of problem. We've seen them before, okay? I wouldn't set u equal to the argument of a trig function here, even if it was something other than one single x. It's one single x here, so it's a moot point. I'd set u equal to the base of the numerical exponent. I'd set u equal to sine x. Remember, du... Remember, when you have cosine and sine together in an integral, 99% of the time, take the one that's raised to a visible power, say it equal to u. It's usually the way to do it. Now, du divided by the derivative of u is equal to sine x. Make sure you know what world you're in, okay? The derivative of sine x is positive cosine x. Crank, but this knife that you just stuck in your back, Mr. Bordeaux. No. That was in the world of integrals. This is in the world of derivatives, okay? In the world of integrals, sine is a bad guy, okay? The police are looking after him, and then they're chasing him, you know, and then he gets to the border, he crosses over the border into the world of derivatives, and suddenly the cops catch up with him, you know, and they put him in cuffs, and he's like, wait, you got the wrong guy. I'm the good guy now. Anyway, so here, remember, whenever you use U-substitution with the definite integral, it's tres substituciones, okay? So the cosine x, well, he's still there, but not for long. He's going to get canceled out. This guy becomes a u squared. Take out the dx. Here's my second substitution, right? Make a du over cosine x. And now I got to change the bounds, that third substitution. You got to know some trig. When x is 0... u is equal to the sine of 0, which is 0. Yay, we kept that 0 bound. And when x is pi over 2, u is equal to the sine of pi over 2. And what's the sine of pi over 2? 1. All right, so maybe it made the bounds a little bit easier to deal with right there. The cosine x's cancel out. What's an equivalent integral? The integral from 0 to 1 of u squared with respect to u represents a different situation from what we started with, but it's an equivalent integral. The exact same answer is what it represents, okay? By the way, integrate u squared, u cubed over 3. Don't put plus c, evaluate it from 0 to 1. And these are u bounds, okay? So you could actually plug in for u. So 1 cubed over 3 minus 0 cubed over 3, which is just really 1/3 minus 0, which is 1/3. So really, it's just practicing more stuff, okay, with the definite integral. You know, make sure you know how to integrate in the first place. Integrating, I don't care how good you think you are at it, you have to practice it, okay? It's more difficult than you might think. Search your feelings, you know it to be true. And you probably in AP land the last 2 weeks, you know, let's get back here, folks, okay? This should be one of your more important classes to close out the year. This one's kind of cool. You know, how do you integrate e to the x? Don't do anything, right? You just get back e to the x. But in this case, we're going to evaluate it from ln1 to ln6. You know, people are like, wait, why are there ln's there? That's so weird for the bounds. Yeah, but that's great because when you plug in, right, you know, you get e to the ln6 minus e to the ln1. What do e and ln do to one another? Destroy each other. Very good, okay? They cancel each other out, and you're really just left with 6 minus 1, which equals 5. So it's a very, very easy definite integral. You even could have took this ln1 and made it equal to 0, right? Now this is 0 right here, which means this would have become e to the 0, which is still equal to 1, okay? So multiple ways to do these problems. So transcendental functions are going to be involved as well, just like number 6, okay? Classic problem right here, definite integral. So what? We just worry about integrating it first. How do you integrate 2x over x squared plus 5? Do you remember if you're integrating a quotient and the bottom's not being raised to a visible power? Try the ln trick, okay? You could set the bottom equal to u if you want to, and then you'll end up integrating 1 over u. You get back ln absolute value u, not necessary to use plus c. You'll change your bounds. You'll still get the same answer we're going to get right here. But if you use that trick which I really hope you tried, okay? It's really just a controlled mental integration, by the way. Mental integration really starts to shine around here because then you don't have to worry about changing the bounds and putting in extra work. You just use those original bounds because you're going to go right to what the integral is, and you're not going to introduce a new letter. The derivative of the bottom is 2x. Remember, if you integrate a quotient and the bottom's not being raised to a power, or it's being raised to a power other than 1 is really what I mean. If the derivative of the bottom is the numerator, you can go right to saying the answer is ln absolute value of the denominator. We used to say plus c, but now we're going to evaluate it from 1 to 2. No need to change any bounds because we didn't use U-Substitution. We used integration by observation, which is really just mental integration. Remember, if that was just an x up there, you could still multiply the derivative of the bottom by a 1/2 to create the top. So you put a little 1/2 right there. Don't forget that trick. You know, this becomes really cool now. ln, let's drop in that upper bound. So 2 squared is going to be 4 plus 5. So ln 9 minus the ln of, plug in that 1. So what is that? 1 squared plus ln of 6. All right. So believe it or not, ln 9 minus ln 6. That's an acceptable answer. Sometimes you see stuff like that in multiple choice. Sometimes yes, sometimes no. Okay. Probably what they would do is if you subtract 2 ln's, remember you can condense it into one single ln. If you divide their arguments, they probably wouldn't have ln of 9 over 6 because they'd probably make it ln of what? Divide 3/2. Okay, not a bad answer, ln of 3/2. They don't technically, usually like to do ln's, though, with a fraction. So a lot of people make it ln 3 minus ln 2. These are all doable. These are all acceptable. This one's probably the best one. This is a little antiquated these days. They don't have you do this quite as often. And remember, if it was a part 2 problem, you just leave it like this. You wouldn't have to simplify it. But things like this still do show up from time to time. And I get it. They can be a little bit annoying. Let's try one more problem before we dismiss. Okay, number 7 over here. There's actually 2 ways to do it. Okay, this problem can get a little bit frumpy. Actually, this one really can't get all that frumpy. But there are other problems. There's one that's going to show up for homework. It's going to be really filthy. I think it's number 8 on your homework. If you do it mentally, it makes it a lot easier. A lot of people here, they'll be like, okay, let's integrate e to the 2x. Let's set u equal to the exponent of e. His argument's not one single x. We did lots of problems like that last chapter. Du over the derivative of u, which is 2, is going to be equal to dx. And don't forget, tres substituciones. Okay, you got to change those bounds. When when x is equal to 0, u is equal to 2 times 0, which is still 0, so we're loving it. But when x is equal to ln 2, u is equal to 2 times ln 2, that's 2 ln 2. Okay, and then this right here, instead of e to the 2x, now that's e to the u, and then take out the dx, put it in a du over 2. So lots of different things you could do right here. I'll pull the 1/2 to the side. I'm going to do the integral from 0 to, instead of 2 ln 2, I'll write ln 2 squared. Hopefully that doesn't bother you too much. It means the exact same thing. There's a reason I'm doing that. You might be predicting that. Here's e to the u du, and you have your equivalent integral, okay? Whether you want to put 2 ln 2 here, or ln of 2 squared, or ln 4, here it's 1/2. Integrate e to the u, that's easy. You just get e to the u back, right? Evaluate it from 0 to, I'll even say ln 4. Now you can see it's a little bit easier with the ln 4, because when I plug in, this 1/2, you kind of have options. You could attach the 1/2 if you want and make it 1/2 e to the ln 4 minus 1/2 e to the 0. Or you could leave that 1/2 outside and do e to the ln 4 minus e to the 0. It's really up to you. It gives you the exact same answer. But here you can see this gives us 1/2 times what? 4 minus 1. So 1/2 times 3. Going to give us our answer of 3/2 right there. Okay, so I took that 2 ln 2 so that the e and the ln could cancel out. I rewrote it to ln 4. So be careful, because you might just have an e to the 2 ln 2 right there, and you're like, well, what the heck do I do now? You look in your answer choices, you're like, 3/2. Where'd that come from? So you got to be able to manipulate as always, okay? Mental integration actually makes this a lot easier, and this is a great mental integration situation. Think about mental integration. I mentioned it before. U-substitution is kind of like the opposite of the chain rule for derivatives. Chain rule, we multiply by the derivative of the inside. U-substitution, we divide by the derivative of the inside. It's still very dangerous. If you want to be in BC calculus, you should be thinking about it because it really speeds things up. But really, you can get through all of AD calculus with a 5 without really worrying too much about integrating mentally. The only mental integration I really think you should know is this one. Okay, but we have a whole setup system for that, right? It's like controlled mental integration. So I don't really call it the same thing. But anyway, over here, you know, if you want to integrate e to the 2x, like, you know, you're getting e to the 2x back. But now, instead of multiplying by the derivative of the inside, which would be 2, you want to divide by the derivative of the inside. So you want to divide by that 2. Can't tell you how many times they'll have a 2 in front in the multiple choice or an answer that represents that 2 in front, and people will get that wrong because they multiply by the derivative of the inside. It's integration. It's the opposite of differentiation. Do not multiply by the derivative of the inside. Divide by the derivative of the inside. And then we could just take this answer, evaluate it from 0 to ln2. And this is really 1/2, right? Like before, or even, do we want to keep let's keep the 2 down there just for the heck of it. So many different ways to do it, right? Here, this becomes e to the 2 ln2 divided by 2, minus plug in the lower bound, e to the 2 times 0. Leave them right at there. And this, you know, you still gonna have to play around. Like, how do you simplify this? Well, this is e to the ln of 2 squared over 2, minus this is just e to the 0 over 2, and this is equal to e to the ln of 4 over 2, minus 1 over 2, and this right here is going to give us 4 over 2 minus 1 over 2, which gives us that 3 over 2 that we got before, okay? Integrating mentally can be useful. Here, doesn't really make that much of a difference, okay? So I'm telling you, if you don't want to integrate mentally, don't integrate mentally, okay? If you're a BC, you know, hopeful for next year, you should think about it. And this is actually one of the best situations where you have e raised to a linear. It's one of the best situations to integrate mentally because weird things can happen. You know, when you divide by the derivative of that inside, it really happens before the integration takes place. You need to realize that things are going to cancel out. It's like a lot more difficult to integrate something like this mentally. So try not to worry about that so much at this point in time, but please practice these problems, okay? Watch these videos. Don't slack off, okay? Next year, regardless of the way it's going to happen, folks, okay? And I really hope I can see all of you right away. Who knows, okay? You know, hopefully things will be a lot better by then. But look, by the end of the year next year, we're hoping things are much better. You're going to have advanced placement exams to take. And don't be the kid who takes BC calculus and doesn't even bother to watch my videos or put in their work. It's a whole work ethic thing. I'm telling you, you could be a really smart kid, but if you're in BC calculus, we're going to move so fast. If you don't put in your work, you're going to struggle, okay? So please, if you're taking BC, please put in your work and take it seriously. AB too. Don't think AB is the joke of the year. It's a very difficult course, okay? So look, if you want to take those courses, you got to have your butts in gear. I get it. As I've said on so many of my other videos, you got things going on right now, you know, outside of your control. Totally understand it, okay? Life is life, you know, and you will get back to where you need to be eventually. But, you know, if you're just sitting at home like, you know, I just want to Snapchat all day, well, get some work done, okay? Anyway, so that's another lesson. That's Wednesday right there. 2 more days this week. I think we'll start doing Google Meets maybe for extra help. So I'm thinking Thursday is going to be my time, but the administration, we're still speaking about that back and forth, but maybe we'll get one of those going on tomorrow. Kind of thinking Thursdays at 9 a.m. I would like as a time, but we'll see, okay? Anyway, this is Berto signing off, okay? So, you know, really just the definite integral with some different types of problems. Remember, it can represent the area between a function and the x-axis. It could also just be problems that you have to worry about mechanically, okay? And I will see you all tomorrow. Adios. Take it easy. Goodbye.